I'm happy to introduce Paul Schechter today. Dan Klepner is here with us, but he has adroitly passed the job of introducing Paul onto me, and I'm happy to do that. Paul is I was impressed to read that you're an observational cosmologist. You know, that I can see that observational astronomers have been elevated. It's like going from cardinal to pope.
Indeed. I never use that word to describe myself.
Oh, this is MIT.
Indeed, I don't even use astrophysicist. For me, when people say astrophysicist, the physics is a fig leaf, and I have nothing to hide.
Astronomers should always be elevated. I mean, geologists might not be.
So anyway, so we'll say that Paul is an observational astronomer who did his undergraduate work at Cornell. And I suppose, were you influenced by Carl Sagan? Because he was certainly there at that time.
Not at all.
Not at all.
The heaviest influence was a high energy particle physicist, experimentalist. And I set out to Caltech graduate school. I'm stealing your introduction.
Go ahead. No, you're doing my job for me.
To be a particle physicist, and after a year, switched to doing straight astronomy.
Well, that's very tempting at Caltech because it certainly was all around the place. So he got his bachelor's degree at Cornell in 1968. Went out to Caltech. Finished up in 1974, but his degree is awarded in 1975. If you like the details, did a postdoc at the Institute for Advanced Studies. I didn't know people did postdocs at IAS, but there you go. University of Arizona. These are all premium sites for doing astronomy. A while at Harvard, and came to MIT in 1988.
I like to say I've been fired from all the best places.
Well, what is it? With enthusiasm, I hope. A distinguished emeritus professor, and he has done work on lensing. Oh, I should mention he's a member of the National Academy of Sciences, which is a fairly high honor, and had a Guggenheim one year. Where'd you go with that?
I went to the Institute for Advanced Study.
Back? I mean, was that?
The Institute for Advanced Study calls everyone member, and so there are members who are postdocs, and there are members who are senior people looking to recharge their batteries. So everybody is a member.
Okay, very good, and then he has done this work on a variety of subjects, but the one, of course, that's of interest, I think, particularly to us today, and certainly to me, is gravitational lensing, and but using gravitational lensing for various analytical purposes, for sort of probing the universe, I think, finding mass scales of galaxies, and these are the kinds of things that he does. But one of the fascinating mentions, again, it may be just MIT PR, says that you helped develop and implement active optics on the 6.5 meter Magellan telescopes in Las Campanas.
It turns out that this gravitational lensing game, you're looking at things that are very, very small, and you need really good image quality. And so you just have to make that telescope do what it's supposed to do. Now, in fact, it's not rocket science making a telescope do what it's supposed to do. You just have to do what you're supposed to do in the course of that. So yes, you can get the images that the atmosphere is giving you. This is not correcting for the atmosphere if you're careful, and that's what we did. But I'm proud of having done that. That telescope produces great images.
Well, it also involved repurposing a broken mirror from a larger telescope, did it not? I mean,
not this one.
Not this one? Oh, yeah. Okay.
Oh, that was Michigan Dartmouth MIT Observatory. But yes, that's where I got my start.
Well,
on
they
that.
say the mag AO. Are we talking about mag AO?
No.
Okay.
So AO is used mostly these days for adaptive optics, which compensates for the atmosphere. Active optics compensates for gravity and temperature.
Okay. All right. Well, anyway, I'm learning lots from introducing you. You see, it's good.
It's the idea, right?
Yeah, right. Good. So today, Paul is going to talk to us about Einstein rings, but I hope he's going to tell us more so that we understand what an Einstein ring is. And he's already taught me a little bit about that in editing his abstract. And I turn it over to you, Paul Schechter from MIT.
Okay, well, thank you for the opportunity to talk. And hello to those of you. Is that in a library there?
That's in the community center.
You said it. Hello to everyone in the library.
We're here with a little crippling. We're here.
Okay, so let's proceed and let me tell you about Einstein rings. And I'm going to click on share screen, and we'll see if that works. Okay, just a second. Let me not start in the middle. I was rehearsing my talk, and so I was in the middle of the talk in the shared screen. So let's go back to the beginning. Okay, now I'll go back to sharing my screen. Here we go. Okay, so as you can see, this is a talk about Einstein rings. And the image that you see on the left is an image of the first Einstein ring discovered. It's actually a radio image, with a false color intensity. So it was taken with radio telescope. Most of what I'll be talking about is optical imaging because that's what I do. And in fact, we see more. They're both of use in studying Einstein rings, but most of the work has been in the optical rather than the radio. But that's the very first one. And the Einstein ring that you see on the right tells us something as well. It tells us that there's enormous cachet associated with Einstein's name, and everybody wants to associate it with themselves. This particular ring is on sale for $30 from a website that caters mostly to bikers. And most of their rings are skulls and crossbones and lightning bolts, but they also have an Einstein ring for bikers who are fond of Einstein. But the point here is that Einstein's name has enormous cachet, and so everyone wants to cash in on it. So astronomy is an observational discipline, and what happens is that we find phenomena that we don't understand, and we get excited, we carry out observations, and we find more examples after the first example, and we slowly assemble collections of data, and we begin to draw conclusions based on what we're seeing. And I would sort of like to follow that approach in what I say today. So we'll start out by just looking at what people have called Einstein rings and making some observations and drawing some tentative conclusions and making some mistakes along the way and then correcting those mistakes as we go along. So we'll recapitulate history here to some extent. So I found a very nice graphic that NASA had prepared 20 years ago now, showing a montage of 8 objects that a group of investigators called Einstein rings. And so let's take a look and see what those Einstein rings look like. These are all images taken with the Hubble Space Telescope. Did that change?
Yep.
Good. So here are 8 images taken of galaxies. There are 8 things that were called Einstein rings. And if you look at this for a minute or two, you immediately draw some conclusions. One is that some similarities, you generalize from 8 examples. You say, oh, there's always a yellowish thing at the center of the Einstein ring. And that yellowish thing is a fairly massive galaxy. And it's typically, the universe is expanding. And it's typically receding from us at perhaps a quarter of the speed of light. And so, in fact, if you were to look at this in true color, it would not look yellow, it would look redder. But NASA has done us the favor of taking the redshift out of this diameter so that the central galaxy looks yellow like the sun instead of redder because of the redshift of the sun. Universe is expanding. Things that expand shift to the red, but it's been taken out. We know this because in addition to imaging, spectroscopy has been done, and we can recognize the lines of elements that are shifted by 25% or more of the speed of light in the galaxy. And then surrounding these yellow lensing galaxies, they're called lenses, we have some blue arcs, and they're very curved, and they're quite blue in contrast to the yellow galaxies. They are also galaxies. They're galaxies whose velocities of recession are on the order of 2/3 the speed of light or 3/4 the speed of light. And the light from the blue arcs has been traveling to us for about 1/2 the age of the universe. So that's 7 billion years among friends. So there are, in each of these images, 2 galaxies visible. A yellow-orange one, which is the lens, and a very blue one. Now, that very blue one, the light that we're seeing is actually in the ultraviolet. And so these galaxies, the ones in the background, are very bright in the ultraviolet, unlike the yellow ones, which are kind of dead in red, except they're presented as, galaxies which have undergone recent bursts of star formation have a lot of young, hot blue stars. And that's what you're seeing in these rings or arcs that are surrounding our lensing galaxies. So let me start accumulating a list of common attributes of these things. There are yellowish blobs at the centers, and then there are bluish arcs along the periphery. Let's go back and let me ask if one notices anything else about these things that strikes them. Anyone see anything that just seems like it's a more or less common feature? Generalized on the basis of the square root of 8?
One thing that I see is that there are some blue stains on the bottom row, third one to the right, which are in the disk, inside the disk, as opposed to, that one to the right.
So that blue stuff is part of the galaxy that's behind it. It's just that the ring is not quite circular. It bends, and so this bit over here actually corresponds to this bit over here. And we'll see more about that. But there tend to be pairs of blobs that oppose each other in these things. Not quite opposing, but here's a blob and here's an associated blob. And actually, there's another blob over here associated with that. And again, there are blobs in a number of these things. And there tend to be multiple blobs around the periphery. So that's another observation, a good one. Anything else?
Are you noticing that they're paired? That is.
Yes. And sometimes they're actually quadrupled, but paired definitely. Anything else? I mean, you can be an astronomer because you don't have to know anything. You just look and say, hey, here's a bunch of things that look alike.
And I qualify.
That's right. Okay,
well, some of the images.
You'll notice that this one in particular.
Some of the images I was going to say look irregular, while some others are very symmetrical, like the bottom row second to the right strikes me as having a nice ring, as well as the one all the way to the right. But, you know, while the others don't have exactly the same symmetry.
Right, right. But this one in particular is definitely not circular, and it's slightly offset from the center. And this one, again, it's definitely not circular, the ring, and is offset from the center again. And it's got two bright spots, one on either side, although it is pretty smooth. So you're doing a good job. You could all be astronomers. Great.
Some of them have more than one ring.
Yes, because there could be two galaxies in the background. So there are those, and those are very special. So anyway, here's our list of attributes, and we've added a few more. The arcs are sometimes non-circular. There are brightness variations within the arcs, both smooth variations and blobby, and the arcs often don't close upon themselves. So we've got a bunch of phenomena we'd like to explain. The montage that I showed you, you might have been wishing that I would magnify it a little bit so you could look a little more carefully. And you would find that actually seeing just about everything that the space telescope images could bear, and you'd start seeing the pixelation. Instead, I'm going to show you an example which shows more detail, and it shows more detail because it happens to be have a bigger diameter on the sky. And so it's a very beautiful one. It's called the Horseshoe Ring. And here's the Horseshoe. It's about twice or 2.5 times the diameter of the ones that you saw in the previous image. And so the details stand out considerably more. There's a penalty in the end that you pay for having a larger ring, and I'll tell you about that in a bit. But we're going to return to this example, and I'm going to show you the results of an effort to understand what's at work here. But we're going to have to work our way up to understanding what's at work. And so we're going to start at the basics because I'm told that you all don't are not students of physics and astronomy, and I suspect that you know much more than you admit to. But I'll take you at face and describe it to a non-special, as I would to a non-specialist audience. So this, if you're going to burn one picture into your memory, this is the picture to burn into your memory. It's called the Horseshoe. You can find it by looking for the Horseshoe Einstein Ring, and it's a great one. And even if it weren't interesting scientifically, it's beautiful. So for that reason alone, one to remember. So I said
it's horseshoe because it looks like a horseshoe, or is it in the horseshoe?
Yes, it's broken. It's broken at the top. There's nothing up here. It's not. I cut it off in part because there was just nothing up there, and I wanted it to be as big as possible. But no, there's no light up here. Very little light. So it's a broken, and the fact that it's broken is important for understanding what's at work here. So astronomy does not proceed. Progress in astronomy is not straightforward. There are steps. There are steps forward and there are steps backward, and it's often in the case that in our first encounters with astronomical phenomena, we jump to conclusions and we make mistakes. And so we have to back up and rethink things. And that certainly was the case when we discovered gravitational lenses. In fact, the French were much more circumspect, and they called the phenomenon gravitational mirages, mirage being a good French word. And that more accurately captures the physics that's at work than the word lens. As lenses go, these are pretty awful lenses. So let's take a look at a really good terrestrial mirage, probably better than any of you have ever seen. So here's a terrestrial mirage, and it's quite interesting. It's complicated, but what you know about mirages is that you see multiple images, at least one image distorted, and very often multiple images due to variations in the index of refraction of the Earth's atmosphere. What you've got is you've got an inversion here, and the index of refraction down here and in the inversion is much higher than up here. And so because of the variations in the index of refraction, we actually see at least two, and you can argue three images of what we're seeing here. The other thing, one of the things to note about this thing is that the handedness of these images is reversed. If we call this image down here a right-handed image, then this image here is a left-handed image. There's no way you can rotate this image to get this image here. You know, it's like you can't rotate your left hand on top of the right hand and get them to line up with each other. They have a different handedness. So we'll call images that have the quote-unquote correct handedness right-handed images, and the ones that have the incorrect handedness, they're unnatural handedness, left-handed images. The key to understanding mirages, both of the terrestrial refractive and gravitational form, is something called Fermat's Principle. And Fermat's Principle, we learned twice. We learned it in high school, and high school tells you that light travels along paths that minimize the light travel time. And then we learn it again if you take a university physics class, and I suspect some of you have. I call it university physics in homage to Sears and Zemansky, whose textbook many of you may have used. In university physics, you learn that not only are minima of the light travel time, do minima of light travel time to determine where the light path, but maxima also give images. So you can see images at maxima. And you can also see images at saddle points. Saddle points are places where you're looking at a scene, and it's, as you see it, it's two-dimensional, projected on one eyeball. And saddle points have the character that you have a minimum in one direction and a maximum in the other direction. So they're curved like a saddle. The time, light travel time, is shaped like a saddle. And the minima and maxima preserve the handedness of the original image, whereas saddle points flip the handedness of the images. So what does this have to do with gravitational lensing? Well, when you talk about Fermat's Principle, you're talking about refractive indices and the index of refraction slowing down the light as the light travels through a medium. Light coming to us through space, it's not going through any kind of refractive medium. So this is the only place where the theory of relativity comes into play in gravitational lensing. For the most part, you can do everything you need to do for gravitational lensing with Newtonian physics, with one exception. And that exception is that in general relativity, light experiences what we call an effective index of refraction that's proportional to the strength of the gravitational potential. Now, gravitational potential is a concept that you don't encounter in high school physics, but the idea is that in the same way that the electric field is the derivative of an electrical potential, the gravitational field is the derivative of a gravitational potential. So and it's related to the potential energy in the same way that the electrical potential energy is related. So this is a consequence of general relativity, a strictly theoretically derived consequence, one that was not expected, that gravitational potentials slow down light. And as a result, Fermat's principle comes into play when we look at images of objects that lie behind some gravitational potential due to an intervening galaxy in the cases that concern us. Does anyone have any question about this or comment?
So these have to be big, right? I mean, there has to be a large gravitational potential. Or
no, actually, that's what's amazing. You know, the angles through which the light is bent in these lenses are measured in tens of microradians, small numbers of arc seconds. And so the bending is very, very small. And the gravitational potentials are typical of the gravitational potential near the surface of the sun. You know, so they are, from the point of view of how relativistic is this. Go ahead.
Now, I know that there are lots of large things out there and even more large spaces. So if you're looking at something out far, far away, how likely is it that the light coming from it is going to go through a huge gravitational mass? Will that happen most of the time?
Well, these are not huge gravitational masses. They are typical of galaxies. But nonetheless, galaxies cover a very small fraction of the sky. So you have hit upon perhaps the biggest problem associated with gravitational lensing, and that is it is a really rare phenomenon.
Okay, thank you.
And so I knock my brains out trying to find these things. If it says my internet connection is unstable, are you hearing me?
Hearing you fine now, but about 30 seconds ago, it waffled.
Okay.
Yeah, there are occasional dropouts, but we're getting most of it.
Yeah, it's working.
Okay. I just changed my modem last week. Comcast threatened to cut off my internet if I didn't. So I got it working for this. So what I spend all my time doing is figuring out clever ways to find gravitationally lensed objects when a random source sitting out there halfway to the edge of the universe has only a 1 in 1,000 or 1 in 10,000 chance of being gravitationally lensed. And so it's very much a needle in the haystack problem. And you need to have some clever way of finding these things. And I've tried various things with only modest success. But yes, that is the biggest problem associated with gravitational lensing is just finding these things. Okay, so let me do an example of Fermat's principle in action.
Quick question.
Okay, so I have a question. Will gravity pull light that is approaching, thus increasing its speed? And this gets to the heart of this light experiences an effective index of refraction issue. If you go into fine detail, what you find is that at any point in the universe, gravity always travels at the speed of light, no more and no less. Any observer, anywhere. So if you've been pulled into one of these gravitational potentials, if you're in there, this light still travels with the speed of light. But what gravity does is to warp the space-time. And so the path in the space-time, because of that warping, is longer than the path would otherwise be. It has to go down into the potential and back up And so it's traveling further. And so as a result, it is delayed getting to you. So it is the warping of space. But this business of light experiencing an effective index of refraction represents an integration summing over the entire path and asking by how much the warping of space-time has increased the path length. And then that's an effective index of refraction. How did I do?
I thought that was really good.
Thank you.
Yeah, even as someone who's not even trained in this area, I can visualize what you're talking about a lot better now.
Great. Onward.
It's good old Star Trek.
So let me show you an example of Fermat's principle at work. Here we are. What you see is light traveling from Newark to Brighton, and I'm assuming most of you are locals, and it's almost on a straight line, passing through Boston, and this Google Maps was produced on a Sunday morning, and there's not much traffic, and the blue path, Google is telling you that the blue path is the shortest travel time. The next slide is going to show the path that Google chose on a Monday morning during rush hour. And on the Monday morning, there is an effective index of refraction, a medium that's slowing down the travel of vehicles. That medium is other cars, but it's going to take longer along the direct path. So in Google Maps, they say, let's take the shortest path following Fermat's high school version of the Fermat Principle. And in fact, Google Maps says you want to take Route 128 and avoid Boston proper, as you would avoid if you were like a gravitational lens, because it would take more time to get through that gravitational potential. Now, the exaggeration here is that everything happens, the size of the gravitational lens is 1/10,000th or 1/100,000th of the distance here. So it all happens in a very small area. But when you look at it, you say, oh, this guy's coming from Waltham, you know, when you get in the plane of Boston, rather than saying he's coming from Newburyport. In fact, he went from Newburyport to Waltham and then from Waltham to Brockton to take the least possible travel time. So that's Fermat's principle, except instead of there being a refractive medium, cars or glass, you have a gravitational effective index of refraction, a slowing down. Now, the way progress proceeds in astronomy is to make models, and you see how far you can get with the simplest model, and then when the simple models fail, you make more complicated models. But I'm going to show some highly idealized models of gravitational lenses and how they affect the travel time, and that will help us to understand, on our way to understand the horseshoe. So here are 4 highly idealized instances of gravitational lenses. What travel plotted in all cases is the light travel time increasing vertically, and the 2 horizontal directions are position on the sky. What we imagine in this case over here, there is a source right over here at 0, 0, directly above 0, 0, and no gravitational lens whatsoever. This is like the first picture of Boston. So the light just goes straight through the center. And what we're plotting here in the middle, why doesn't the light go here and then bend and then come to us over here? And the answer is because the minimum of the travel time is here. And so it knows that if it went over here, the travel time would be longer. This surface, by the way, is a paraboloid, but it is cut by the it is cut by the intercepts, the axes, and so it has this funny shape, but it is a section of a paraboloid of revolution. Now what I'm going to do in the next feature, over to the right, is we're going to introduce a circularly symmetric gravitational lens. And we're not going to put it directly along the line of sight. We're going to offset it to the right. So I know this doesn't look circularly symmetric. It's the finiteness of the grid, but it's circularly symmetric. What's happened is that the gravitational potential decreases as you go away from it, but it's still finite over here at 0, 0. And so the minimum of the travel time now moves over here. And so the light over here goes outward, goes to the minimum, is deflected, and then goes to us. So the minimum of the travel time is moved in the same way that the light traveled through Waltham instead of through Boston. Now, this introduces a phenomenon. You remember that I said the light travels along paths that are minima, maxima, and saddle points. Over here, on the back side of the circular lens, the gravitational potential decreases in this direction, and then the travel time increases because of just the extra travel time of the going out of your way. But in this direction, the travel time has a maximum. So you have a minimum in this direction and a maximum in this direction, and that's one of these saddle points that I was mentioning. So you're going to get a second image over here at this saddle point of light travel time. With the handedness flipped, it'll be left-handed. And then, wait a minute, there's a maximum over here. Shouldn't there be a third image? And the answer is, yes, indeed, there is a third image, at least in principle. But something that I haven't said, but I need to say for the sake of completeness, is that the images that we see are either stretched or compressed, magnified or demagnified, depending upon how quickly the minimum ceases to be a minimum, how fat the minimum is. So over here in our minimum or saddle point or maximum, over here in our minimum, the travel time doesn't change very much as you go around here. And so the flatter you are, the more you're stretched, and whatever image you have over here gets stretched out in this direction along an arc. It gets stretched less in this direction because it's less flat going in this direction. So the derivative of the deflection is smaller in this direction and larger in this direction. And so the magnification is proportional to the flatness of the light travel time in the vicinity of the minimum, maximum, or saddle point. Up here at the very center of the galaxy, the light travel time changes enormously rapidly because you're going through the very center of the galaxy. So that's the light travel time surface is not at all flat. And so the images are either very, very demagnified or completely gone, infinitely demagnified. So while in principle you expect to see 3 images, usually you see just 2, although there are rare cases where we see a third image at the maximum. Any questions about that? Okay, onward. Here's Waltham. Now what we're going to do, we're going to take this, and it's circularly symmetric. I know it doesn't look it. We're going to take this circularly symmetric gravitational lens, and we're going to move it right in the way of the background source, right on the axis, 0, 0. So we'll have to go directly through the gravitational lens. That's over here. And you can see what happens. Because it's symmetric, because the lens is lined up with the source and us, the observer, all of the light paths around the outside have the same travel time. There's no reason to prefer this one over this one. It's all symmetric. And so this is actually flat in this direction. There's no derivative to the travel time. And the source is infinitely magnified along a circle in the plane of the gravitational lens. And this guy over here is a perfect Einstein ring. But you got to be perfectly aligned. If you're not, you get one image on one side and one image on the other side. So here is a perfect Einstein ring, and this is what you need to happen to get a good Einstein ring. So not only are these things rare, but they're doubly rare because they have to be really well aligned. And then off to the right, I'm going to show you something which has more to do with what interests me than what interests you, but they do appear in Einstein rings, and they help to find Einstein. What we've done here is we've taken this offset gravitational lens, and we've made it elliptical. Gravitational potentials are flattened, galaxies are flattened, and so the gravitational potential is no longer circularly symmetric here. It's higher along this axis than it is along the other axis. As a result, this extra gravitational potential, let's say you're looking at an edge-on galaxy, this extra gravitational potential now introduces a ridge in the light travel time because there's extra light travel time. And so you have a saddle point over here. It's a minimum in this direction and a maximum in this direction, and then two minima. So by flattening the gravitational potential and making it non-circular, you can sometimes produce 4 images and not just 2 images. How am I driving? Am I hitting traffic?
When you say 2 images, you mean 2 blobs, not 2 rings, for example.
No. I mean, over here when I say, I'm assuming, this assumes an infinitely small point source. And I'm about to, in just a second, consider what happens when the source is not infinitely small. When I say 2 images, I mean something incredibly small. You can't see with a telescope. Likewise over here. So 2 point images with a 3rd image. But the point image, even though it's incredibly small, still can be magnified in this direction or demagnified in both directions. So right now, I'm just talking about a point image here, a point image here, a point image here, a point image here, and a vanishing point image here. Okay, brings me to the next question. What happens if we have a finite source, not a point source? Then we have to make a bunch of different diagrams with the source at different places and superpose them and see what we get. And I've again made a model of that I show in the next image. This is a complicated drawing. This is the first time I've made it, and it doesn't show everything that I would like, but it's a start. So here we have the center of a gravitational lens, this orange dot, and I apologize to the color challenged among you. And then offset from this, we have a galaxy of finite size with the magenta representing the outermost edge of the finite sized source. So this galaxy here is going to gravitationally lens this source over here. And for every point along the magenta ring, for every point along the pale blue cyan ring, for every point along the green ring, I have to go through the procedure in the previous slide and figure out where the images are. And I've plotted them here. So here you see the image of the magenta ring. Here you see the image of the green ring. And the smaller the ring in that source is, the smaller the arc. Now, I've been very cagey here. I've drawn the magenta ring so it just grazes the center of the galaxy. It doesn't quite pass through the center of the lens. And as a result, these two and these 2 points don't meet each other. For the blue, which doesn't get as close, they are even further from each other. And for the green, it's barely extended at all. And of course, I can't draw them any smaller, but as you go smaller and smaller, they become more and more like points. If I'd drawn it a tiny bit larger, the magenta ring would become complete. And it would be a continuous ring. However, the sources that we look at, galaxies in particular, tend to be very highly centrally concentrated in their light. And so even though you have a complete ring in this case, you're going to get much more light from the green than you're going to get from the magenta. The magenta is the faint outskirts of the source that's being lensed, and the green is the bright central image. And so you're going to get this double structure that some of you noticed when we were drawing conclusions. This, opposing spots on either sides. And then, and this brings up, and then there's something that you might notice and might not, and that is that, can you hear me? Can someone tell me that you're hearing me?
I'm hearing you.
But
Thank you. Okay, thank you. Thank you. If you look carefully, you'll see that these arcs, oh, I didn't mean to do that. These arcs, come on. Stop that, whatever it is. Don't do that.
We're okay.
Well, that's okay. No, I don't want that. Okay, these arcs are centered on the source and not on the lens. And so the arcs are offset from the center of the lens. And finally, you can draw a circle around now the lens that goes like this. It comes very close to this magenta here. And then, no, let's do it the other way around. You see this is offset. It comes very close to the magenta on the outside here, and very close to the magenta on the inside here. But that ring, that circle, separates the left-handed images and the right-handed images. These images here are the right-handed images, and they're minima of the light travel time, and these images here are all left-handed images, inverted image parity, and they're saddle points of the light travel time.
Is this light polarized?
Good question. It can be. The gravity doesn't polarize it, but if the source is polarized, and then the question of what happens to the polarization is a wonderful question that one of my colleagues, Bernie Burke, loved to argue with people about. But yes, it can be polarized. And in fact, if it's circularly rather than linearly polarized, the handedness of the circular polarization changes. Okay, so one of the reasons for showing this is that when we drew our conclusions about the attributes of rings, we collected the sample that NASA gave us, and NASA knows what they're talking about, and they were all very, very blue rings. But not all distant galaxies are young star-forming galaxies. And in particular, the lenses that a lot of us work on are distant galaxies that have at their very center something called a quasar, which is very, very bright. It's a black hole which is turning matter and mass into light. And the central quasar can be much brighter than the galaxy in which it lives. These are very, very rare things, but they were much more common when the universe was half its present age than they are now. So this is a way to find, looking for quasars is a way to find gravitational lenses. And most of those quasars don't live in star-forming galaxies. They live in red galaxies. And so it's kind of, in NASA's picture, they looked for things that had blue rings. And it's kind of like drawing conclusions on shoe sizes by looking at a sample of basketball players. You're misled in the mean shoe size that you would find because they were selected to be on the basketball team for having big feet, among other things. So in fact, there are red rings that can be found if you look at quasars that are either doubly or quadruply imaged. And this gives me a chance to show you some of my friends. This one on the left is very tricky. On my computer, you have to tilt the screen so that your head is looking down from the top. But if you look here, I think you can see a red ring extending around here. That is the host galaxy. I would be grateful if I had a show of thumbs or something to see how many people can see this.
It's visible here. Oops.
Okay, good. So there are actually many more red rings than blue rings. It's just that we were looking at the shoe sizes of the basketball team. In fact, these are what we see. This one over here is another favorite of mine. And the background galaxy is neither redder nor bluer than the lensing galaxy in that case. And then this one over here, I'm showing you this because it's a very nearly complete ring. It's very nearly circular. It's actually, it's another beauty, and I just like it. But it's actually a surprise that it's circular. And the reason it's a surprise is that there's not one galaxy doing the lensing, but two. And so we would expect the gravitational potential to be elongated in this direction. And we would expect this thing to be less circular, and it's not. And what that's telling us is that these two galaxies are embedded in what we call a dark matter halo. The dark matter extends way beyond the ring. And it's telling us that the dark matter associated with this pair of galaxies does not have the same orientation as these two galaxies here. And that is both the blessing and the curse of gravitational lensing. It's what makes them interesting. By the way, I'm not
mean that does that mean that the dark matter is much more massive than the galaxies?
Oh, yes. The galaxies are basically the icing on the cake. What we call, this is a terrible thing that astronomers have done. When they talk about galaxies, most people are talking about the stars and gas. They're not talking about the dark matter, even though the dark matter is the reason for the stars and gas being there. The stars and gas would not have condensed if there weren't 5 times as much dark matter as there is baryons and stars in mass. And so the stars and gas that we see are simply the icing on the cake. They're along for the ride, and because the stars and gas lose energy when they collapse, they radiate, they collide, they heat up and cool down, they collapse to the center of the dark matter condensation. So you have a high baryonic concentration, a high ordinary matter concentration at the center of the dark matter, and then you have a dark matter halo that extends 10 or 30 times beyond the Einstein ring here. And it can have a different shape, and does. And that's one of the things that Einstein rings are good for. In fact, my next slide is, so what good are Einstein rings? And the answer to that is given by much better, by Chris Kachanik and his collaborators in the title and a sentence from the abstract in a paper. So I'll just show you what they said. The importance of Einstein rings, 2001 paper. Within the abstract, they say, the shape of an Einstein ring accurately and independently determines the shape of the lens potential, which depends on the dark matter, and the shape of the lens source, and the shapes of those galaxies that have quasars at the center are interesting in their own right. And so it's a 2-for-1. You can both study the gravitational potential of the lens, and it magnifies the background source, so you can study it in detail. So who could ask for anything better? And indeed, a very large number of the papers, a very large number of the extragalactic results that you've been hearing about from the James Webb Telescope involve gravitationally lensed background sources, because you get 5, 10, 20 times as much light as you would get from unlensed sources. So you can do spectroscopy that you otherwise couldn't do. But it's become so commonplace that they barely mention that these things are gravitationally lensed. Okay, any questions? Okay, let's return to our friend the horseshoe.
Yeah, I've got a question.
Okay, yeah.
I believe it was 1996 when my brother was at Bell Labs, they published a paper that talked about the morphology of, oops, let me turn this on. They published a paper that talked about the morphology of lensed galaxies without really knowing that they were lensed galaxies. So where does the transition come from the first observations of these things to people understanding the connection that you've just been describing in terms of how the process works?
This sounds like a guy named Tony Tyson. So we have to make a distinction between strongly lensed and weakly lensed. There is, I'm going to go back here. If you move the source beyond that imaginary circle that I haven't actually drawn here, if you move the source beyond that circle, then you only get one image. You don't get a second image. And the stretching is at most a factor of 2 in the transverse direction compared to 1. And so that's called weak lensing because the stretching is less than a factor of 2 in one direction. And weak lensing can be used to study gravitational potentials even if you don't see the second source. That may go some way to answering what you're talking about. And weak lensing is a very big subject. A lot of people are doing it, but weak lensing is outside the Einstein Ring regime. So I haven't talked about it. So here we are again. We're back. We're back to, I hope you can see it, the horseshoe. And what you see here is an effort to reconstruct the horseshoe. I have to tell you that I had not read this paper before deciding to include the horseshoe. And then after I saw the horseshoe, I stumbled upon this paper and looked at the analysis. And it represents a very earnest attempt to implement Kutchanik's plan to determine the shape of the source and the shape of the lensing galaxy. And so all of these little symbols represent little blobs that have been identified by the observer. The zeros are drawn on top of the blobs, and the X's are drawn where his theory predicts the blobs should be, where his model predicts the blobs should be. And in many cases, the blobs and the zeros and the circles line up pretty well. But take a look over here at this pale blue, or is it cyan, observed blob and model, and then orange, and then yellow. And you see it over here, you see the same pair. And if I weren't in my own way, I think you would see the same pair up on top somewhere, or at least part of the same pair. But look over, oh no, you see over here, you don't see it there. Over here, you see the blue guy, but you don't see the orange guy or the red guy. Likewise, over here, you see the blue guy, but you don't see the orange guy or the red guy. Now, if you see two circles, one of these is this magic "don't cross me," the parity, the handedness changes circle. And yet this arc really seems to be a single object, and it's crossing the circle. That's not allowed. You have to stay either entirely within it or entirely without it, unless you've got a new set of images. So his model doesn't really quite work over here. And in fact, he tried a different model, and that gave him the red circle. And then he might have included the orange and the yellow over in here somewhere, but he'd still run into trouble with this guy crossing over here. So He just doesn't have the model right. And this brings up a problem. This dark matter that we were talking about is not smoothly distributed. It is clumpy. And the big clumps almost universally make galaxies. And so the big clumps can almost always be identified. But the small clumps sometimes don't have baryons. Ordinary matter fall into them, or a little bit of ordinary matter falls into them, and it gets blown out, or it gets swept out. And so they are ghost galaxies. They're smaller, they're not as big as big galaxies, but they're little ghost dark matter galaxies all around in here. And those guys have very small gravitational potentials, but they can nonetheless change things. And so getting models like this right, and this one's got a ways to go, are a way of studying the distribution of dark matter clumps on small scales and the numbers of dark matter clumps on small scales, which is a subject of enormous interest these days. And so this kind of stuff is actually in the forefront of a not tiny corner of astrophysics, using gravitational lenses, and in particular stretched out arcs, to study the small scale distribution, the small scale clumping of dark matter, which may tell us something about the nature of the dark matter.
Can I ask, given the lack of progress, as I understand it, in actually figuring out with any experimental sort of certainty what dark matter is, and then there are these some of the rival Mond theories. Does the fact that there seem to be clusters of things kill the prospect of alternative theories, and it is definitely dark matter, or are there Mond theories that could account for this type of behavior?
I will give you a jaundiced point of view. Mond was invented to deal with dark matter as observed in galaxies. And in galaxies, the dark matter constitutes doubles or triples within the visible parts of the galaxies, doubles or triples the amount of mass. But Mond is hopeless in explaining clusters of galaxies, because the clusters of galaxies have 30 times as much. No, it's not fair. But they certainly have 30 times as much mass as you see in the stars. There is more baryonic mass spread out through the clusters. And so Mond has a scale built into it. It has the scale of galaxies. And so Mond, because it was tuned to make galaxies, can produce galaxies, but it can't produce clusters. And the nail in the coffin, the dagger in the heart, is something called the bullet cluster. Do you know about the bullet cluster?
No.
Okay. So in the bullet cluster, what you see is using gravitational lensing, more weak than strong, you see the outlines of the two clusters collide. The dark matter associated with the two clusters passes right through each other because it doesn't interact much with each other. But the galaxies and the gas, the extended gas, suffers a physical collision, and it doesn't pass through each other. So the physical gas constitutes 80% of the mass in the bullet cluster, 80% of the baryonic mass, and it is not in the same place as the 5 times that dark matter. The gas has been displaced from the dark matter, and it's only a small fraction. And it's the dark matter that's doing the lensing. The dark matter is determined by, and you see 2 lumps of dark matter that have passed through each other, and a bunch of gas which is shocked, and the shock looks like the shock you get from the bow shock from a ship. The gas is coming back. So look at the bullet cluster, and then and I haven't seen any attempt to resurrect Mond in the face of the bullet cluster that doesn't creak and groan under the stretching.
Thank you.
All right, we're doing fine.
Yeah, I have a question. A different, an experimentalist in a different field. Somehow it seems to me that what you're doing here is saying, I can't explain everything that's going on, and therefore it must be dark matter. And you're kind of inferring that the dark matter did this or did that. I'd have to go back and pick apart the examples that you gave. Well, the colliding galaxies, if you will. And you're saying, well, this is what happened with the dark matter. But dark matter isn't characterized that well, is it? Or is this just kind of like something where you, in simpler experiments, fit the data?
So suppose instead of calling it dark matter, I called it gravitating matter.
Well, I don't care what you call it.
No, what you call it? No, this is important.
Yeah.
We use gravity to tell us where there's matter all over the universe, in planetary systems, in solar systems, in galaxies, and in the clusters of galaxies. And the idea that matter bends light is pretty well established, to a part in 10 to the 3, let's say.
Mm-hmm.
The theory is we got it down pretty, when we know what the matter is and see how much it bends the light, it's right, when it's pure baryonic. And we see a lot of bending of light that has nothing to do with matter that we can see. So it is the gravitating matter, it is the invisible matter that, we say, well, we know what bends light, and then I have to add another piece to this. Not only does the dark matter succeed in explaining what we're seeing in lensing now, but the dark matter, and this is perhaps the greatest triumph of the idea of dark matter, the dark matter explains what we see in something called the cosmic microwave background. When the universe was 400,000 years old, it cooled off enough so that what was just protons and electrons in a plasma recombined and formed neutral hydrogen. Until that point, we couldn't see any light coming from beyond there because of electron scattering. It was opaque. But at that moment, we see the universe with the light that was previously scattering suddenly is traveling to us straight from a spherical shell that is 13 billion light years in radius. So we're seeing light coming from a spherical shell, 13 billion light years in a radius, at the moment at which the universe became transparent. So all of a sudden, photons kept going whichever way they were going, and we're seeing those photons come straight at us. We see interesting features in the spectra, in the spatial distribution of those photons. And the features that we see in the spectra, in the spatial features we see in that distribution of photons would not be there if there weren't dark matter, 5 times as much dark matter as there is ordinary baryonic matter. And more interestingly, while the baryonic matter exhibits periodic, and the photons exhibit periodic variations, there are preferred scales for the clumping of these photons. The underlying dark matter does not have those scales. It is the difference between the ordinary baryonic matter and the dark matter that allows the ordinary matter to have these periodic variations. The dark matter doesn't have them. So that is the great triumph, the thing that says there has to be a dark matter and it doesn't interact with baryons. The best the stuff I mentioned is good, but the best stuff comes from the cosmic microwave background.
Does dark matter cluster? In other words,
yes,
the physical matter that we see clusters into galaxies and whatnot.
The dark matter clusters more than the physical. The baryons just go around for the ride. It is the dark matter that is clustering. It does have fluctuations, but those fluctuations are not periodic. They have random phase and random frequency. But nonetheless, where a couple of them happen to be in phase with each other, that forms a condensation. And then the ordinary matter goes along for the ride and falls to the center.
I have to say that I share with Mike Alexander this kind of queasy sense of epicycles. When you start clumping your dark matter into the clumps that will give you your model fit.
The clumps have to happen.
Like the epicycles had to happen.
But if there was no structure at all in the dark matter, if there was no structure at all in the dark matter, then it would be uniformly smooth and it would all keep expanding uniformly. But we see the progressive forming collapse of larger and larger clumps as time goes by, looking backward in time. We see this collapse of the dark matter into dark matter halos with galaxies forming within them. So you might want to look up millennium simulation, and you can see the clumping of the dark matter. It's, now that you do have to have some kind of fluctuation in there, but Alan Guth tells us that this comes from something called inflation, and who am I to argue with Alan Guth?
All right. Excelsior, onward.
Would this millennium simulation paper contain any kind of effort to visualize this distribution?
Yes, that's all that it is.
Okay.
Millennium simulation is, I think, what you want to look for, or alternatively, the illustrious simulation. But millennium simulation of dark matter clustering. You have your choice. There are many different competing versions. So let me finish by talking about Einstein. I have not said much about Einstein. We used his theory of relativity in its weakest.
Excuse me, I'm looking at a blank screen. Should I be seeing something?
Me too, blank screen.
That is intentional.
You're in charge.
The reason that you don't see anything here about Einstein is that Einstein's name is associated with these rings. But the case that Einstein considered was the case of a gravitating star with a star behind it. And he said, well, in principle, if these two stars, and the star is very nearly point-like, and the ring and the gravitational potential of the foreground star is circular, the chance of that star in the background getting close enough to the center of the star in the foreground to produce a ring is vanishingly small. As rare as it is for a galaxy which is extended to reach over and touch and pass around the foreground galaxy, the chance of a star coinciding with the image of a star is yet that much smaller. And so Einstein, who was thinking of stars and not galaxies, yet another example of his short-sightedness, certainly not his biggest blunder, was that he said, well, there's a drawing in his notebooks. And he said, well, this is kind of interesting, except how the hell are you going to get those two stars to line up with each other? And so he dropped it. And there's no reference to the words Einstein Ring anytime thereafter, because he didn't make anything of it. He thought it couldn't possibly happen. When the object that I showed you on the very first slide was discovered, people were very, very excited. And there was another object discovered at the same time. And so both of those papers describing those two objects used the words Einstein Ring in their titles, but they did not use the words Einstein Ring in the text of the papers. And there was no reference to any publication by Einstein, because Einstein never published this because he didn't think it wouldn't happen. And in fact, rings tend to be non-circular and blobby and broken. And so the reason you don't find Einstein Ring, any reference at all into Einstein Ring until the discovery of these two objects, is because it wasn't the thing. These rings are Einstein rings because Einstein's name has cachet. And so you discover something and you got to give it a name that makes it snappy. And you say, oh, this is an Einstein ring. But in fact, Einstein rings aren't Einstein rings. Any more questions?
Well,
So
I mean,
are they
isn't
Schechter
that a situation that applies to any number of namings in physics and mathematics?
And especially in astronomy.
Yeah, but following up on that, I mean, the phenomenon is gravitational lensing, and that was
Correct.
And that was what Einstein predicted.
No question, gravitational lensing was indeed Einstein's prediction, and he made the crucial prediction of the time delay due to the gravitational field. So the fact that the light was bent by twice as much as it would be a strictly Newtonian calculation. So yes, no question, the bending of light, that's Einstein. He gets credit for that. The rings, he doesn't, he considered and thought impossible. The shapes of the objects that were imaged, he didn't consider. He didn't do the details.
I couldn't do everything.
No, he did pretty. He had a good year in there.
Yeah, right.
He had more than one good year.
A lifetime of good years.
Yes. Okay. So, was that your finale?
Yes.
Thank you. That was wonderful talk. And we have some more questions out of the chat.
I can see the chat, so I can try.
All right.
I'm going to stop sharing my screen. I'm a little afraid of what happens there. That's all right. So let me answer Larry Wittig actually, he is next in line. So I knew that someone was going to answer this. Are there cases where a black hole causes the lensings and you get a ring without the right center? These objects are indeed observed. They've been in the news a lot lately. And what distinguishes them from the Einstein rings that people call Einstein rings is that the light does not originate from behind those black holes. The light originates from matter in an accretion disk falling into the black hole. And so the photons are not coming from behind an intervening lens. They're coming from near the surface of the lens. And in fact, many of the photons make complete 360s or even 720, 360s? Yeah, 360s and 720s around the black hole and can go around it several times. These are called photon rings to distinguish them from Einstein rings. And the black hole at the center is in fact a shadow. There's no light coming from there because there's no accretion disk there.
Also, some of the larger black holes are in the centers of galaxies, right? So.
They are, but those are their gravitational influence is still small compared to the dark matter and that surrounds them. And so the scale of those black holes would be not the 2 arc seconds that you saw, but let me try to get this right. Very roughly 2 milliarc seconds. So I have a colleague who's looked into the effect of central black holes, and it's not obvious that they produce anything that is observable. And if they do, it would require a resolution that's enormously beyond what we have right now. Okay. Lensing a ring without the bright center. So those are the photon rings, event horizon telescope. Yes, but that's not what we mean by Einstein rings, and I'm the wrong guy for that talk. Does gravitational lensing produce chromatic dispersion? No. That you know, the effect of the warping of space-time is the same for photons of all frequencies. So it is a uniform delay for everything. So it's achromatic. And that's actually something that we use when we try to discover these things, the achromaticity. I have
I don't know what Tony Galatis's period signifies.
Oh,
but.
Yes, I have a question about that MATLAB figure in which you were showing the source and lens points and then the images.
Yeah, I can go back to that.
Could you go back to that for a moment?
Yes, I can.
Essentially, has anybody tried to make a movie of what happens?
Yeah. Oh, yes.
What happens when you have the two of them converge, and eventually the two half rings, do they become one ring, or do we have a double rainbow kind of effect, but in circles? So
it becomes a continuous ring, but every point within the ring, you know, so the point that comes from over here is not immediately adjacent to the point that's over here.
Okay, is there a place where one can view such a movie, or if nobody did it, can you get a graduate student to do it one of these days?
So the answer is, I can have such a movie made. Since my retirement, I've stopped working with graduate students because I can't make a 5-year commitment, but I've been very successful working with undergraduates. And this is definitely something that an undergraduate could do.
Okay, yeah, it's a simple MATLAB script, I'm sure, but it would be nice to see the evolution of those.
So this is a newly constructed for this talk. I don't know anyone who has drawn this before. And other things that one could add to this is the non-circular lens, in which case the 2 points would not cross each other. They would miss each other. They would be broken because one has to be outside and one has to be inside. So there's much one can do with this. And yes, I could do that. And you're quite right. Why the hell not?
Thank you.
You're welcome. Thank you.
More suggestions for research projects for Paul?
So Ted is now got his found what he's looking for, I think. So go ahead, please, Ted.
Yes. My brother, who was a condensed matter experimental physicist, basically went to work at Bell Labs in the last of the Bell Labs being a sort of national lab era. And then when they sort of started taking Bell Labs apart, he was an amateur astronomer. So they let him go down to South America and play with the big telescopes with Bell Labs financing of it. And he and Tony, as you point out, wrote this paper in 96, and then actually an earlier paper in 96, and then this paper in 97. And they were looking at the different morphologies, just observing what they observed without trying to put any kind of a theoretical model structure around the observations. And at the time, that was considered to be the first paper that actually discussed these observations based on his CV, basically, statement. With your perspective on things, was there work that predated that work in '96?
Yes. So Tony Tyson's own work on this weak lensing phenomenon started in 1980 when he was doing it photographically, of all things. And of course, with the advent of silicon detectors, you got higher quantum efficiency and you got linearity, both of which were major. And then slowly you went from the collecting area of the photographic plate to big devices. And so Tony in particular built the BTC, I think, and it was called. And they went down to Chile and used the BTC to observe lots of the sky. So Tony has stayed with this now for 40 years, and just more and more. So this work almost, I don't know exactly what you're referring to, and there may have been something new in this that hadn't appeared before, but it's part of the course. Tony was the instigator. He was the lab.
Yeah, my brother was at the time before he did that work. He was building both displays and detector arrays using arrays of carbon nanotubes at Bell Labs. And so I guess the goal was to try to build a detector array with higher density of detecting elements, pixels, or whatever you want to call them, and very high quantum efficiency with using the nanotubes as photocathodes, basically using the same technology he was using for displays, where they use the nanotubes as the cathodes, and in this case they would use them as photocathodes, and then have the same use of the electron multiplier technology to allow you to get very high quantum efficiencies.
Well, not only high quantum efficiency, but in those cases you get energy discrimination. And so you can tell not just that a photon landed, but you don't have to use filters. You can tell what the quality was.
Yeah.
That's the appeal of such detectors.
But then he left that. So that he's now working for Google, and I don't know what he's working on because they won't tell me. Much higher security with Google than with any stuff when I was working at Lincoln Laboratory. But in any event, so it sounds like the next step in this process is to try to combine observations at different wavelengths with the same kind of background lensing, and see if you can put together these composites where you have maybe X-rays if you're looking at a quasar or something like that, and maybe the Webb telescope, and maybe some other lower frequencies as well.
Yeah.
Okay, we're getting close to the finish up time, and so I see that Ken Cutter has a question. Maybe you want to look at that.
Can a normal image of the source be constructed from the rings? Yes, very much so. And that's what people do. They make a model, and they project the image that you see through the model back to the source plane.
Back projection now.
And if it's a lousy model, the sources disagree with each other. And so they tweak the model to get the four sources to agree with each other.
So maybe there's some of this model data technology that's being used for the array of telescopes to try to image the event horizon. Maybe that kind of approach can be used for some of these things, because it's very similar process of generating data from models.
Right. Well, generating data from models is has a lot of different flavors, and generating the data from the models involves a hell of a lot of work. And so the people who generate data for the model one kind of thing are probably not ready, not immediately in a position to generate data for a different kind of model.
No, but the software
Ted,
tools they're developing by
Ted, I think we have to come to a halt here.
Right, okay.
So Paul, thank you very much. I mean, it was a splendid talk.
You're welcome.
And
Thank
very
you.
grateful for it.
You're most welcome.
Well, the downside of Zoom is that we can only put up the little hand claps and not the thunderous, stormy applause that Stalin so much valued. But I think you deserve it.